Just take a look around you for a second. The phone in your hand, the car on the road, the actual frame of the building you're in, it's all built with metals. I mean, they're literally the backbone of our modern world. But have you ever really stopped and thought about where it all comes from? How do we go from a chunk of rock in the ground to a massive, polished steel beam? Well, today, let's trace that incredible journey together. Our story actually starts with a mystery. This is the famous Iron Pillar of Delhi. For over 1,600 years, it has stood right there, baffling scientists because, well, it barely rusts at all. And that's an incredible feat of ancient metallurgy. By the end of this explainer, you're going to understand the science that not only solves this ancient puzzle, but also powers our entire modern world of metals. So where does this all begin? You know, the first step in our journey isn't in some gleaming factory or a high-tech lab. Nope. It starts out in nature, with geologists and miners. Because before we can build anything, we have to find the metals. And they're almost always hiding right in plain sight. You see, metals very rarely exist in their pure, shiny form, just lying around. Instead, they're locked away inside compounds within rocks that we call ores. Think of an ore like a treasure chest, right? And the metal is the treasure inside. The whole science of metallurgy is really just about one thing, finding the right key to unlock that chest. But how we unlock that treasure chest depends completely on let's call it the personality of the metal inside. Is it kind of calm and stable, happy to be on its own? Or is it super reactive and clingy, desperately holding on to other elements? Getting this right is the most important rule in the whole game. So scientists have created this amazing cheat sheet called the Reactivity series. It's basically a league table of metals, ranking them from the most reactive all the way at the top to the least reactive at the bottom. This series, it's our playbook. It dictates the entire strategy we have to use to set these metals free. We can break this series down into 3 simple groups. At the top, we've got the highly reactive metals, like aluminum. They are really, really difficult to extract. Then in the middle, you find the workhorses of our world, metals like iron and copper. They're moderately difficult. And finally, down at the bottom, you have the chill, low-reactivity metals like gold. And as you're about to see, these are the easiest ones to get your hands on. All right, so we have our ore and we have our rulebook. Now the real action begins. Let's see exactly how we break these metals out of their mineral prisons, and we'll start with the easiest targets first. For the metals sitting at the bottom of the Reactivity series, the process is, well, it's surprisingly simple. They are so unreactive, so weakly bonded in their ores, that all you really need to do is apply some heat. That's it. Let's take cinnabar, for instance, which is an ore of mercury. All it takes is heating it in air. The heat provides just enough energy to snap those chemical bonds, and out comes pure liquid mercury. It's a process that's almost beautiful in its simplicity. But as we move up to the middle of the series, things get a bit more challenging. For metals like iron and zinc, a little heat just isn't going to cut it. They're way more stubborn. To convince them to leave their ores, we need a clever 2-step process. Okay, so step 1, no matter what kind of ore we have, is to convert it into a metal oxide. Now, if we have a sulfide ore, we use a process called roasting, which means heating it with lots of air. If it's a carbonate ore, we use calcination, heating it with limited air. But here's the crucial thing to notice. Even though the starting point and the process are slightly different, both paths lead to the exact same destination, a metal oxide. So here is that crucial 2-part plan in action. Step 1, make the metal oxide. Then, for step 2, we bring in what's called a reducing agent, and that's usually just carbon. When we heat the oxide with carbon, the carbon is so desperate for oxygen that it literally steals it away from the metal, leaving the pure metal behind. And you can see a truly spectacular version of this process in what's called the thermit reaction. Here, aluminum, which is more reactive than iron, is used to literally rip the oxygen away from iron oxide. The reaction is so intense, it produces molten iron on the spot. It's perfect for welding massive railway tracks together, right out in the field. But what about the kings of the Reactivity series? Metals like sodium and aluminum are just so reactive, they have such a powerful grip on oxygen that even carbon isn't strong enough to break them apart. For these, we have to bring out the heavy artillery, electricity. The technique is called electrolytic reduction. We melt the ore and then pass a really powerful electric current through it. That electricity provides the raw energy needed to literally force the chemical compound to break apart. It deposits the pure metal at one electrode and the other elements at the other. It's basically brute force chemistry. And while it takes a huge amount of energy, it's how we get amazing and essential materials like aluminum. So we've done it. We've extracted our metal, but the journey isn't quite over yet. You see, the metal we get from these processes is often still impure. And even once we achieve that perfect purity, we find out a new, relentless enemy is waiting. For purification, we often use a process that looks pretty familiar: electrolytic refining. We take a block of our impure copper, we call it the anode, and pass a current through a special solution. This causes the pure copper atoms to dissolve, travel through the solution, and then reform on a pure starter strip, the cathode. And all the gunk and impurities, they just get left behind as a sludge we call anode mud. So now we have our pure, beautiful metal. Victory! But for many metals, this purity is also a vulnerability. In the real world, they face a constant attack from the environment, an attack we call corrosion, or, in the case of iron, rust. This classic experiment shows you the culprits behind rust perfectly. In the first test tube, the iron nail has both air and water, and as you can see, it rusts heavily. But in the next two tubes, we take away either the water or the air. The result? The rusting stops completely. It's a simple but really powerful demonstration that proves to cause rust, you need both air and water. And this brings us to the final, crucial chapter in our metals journey: defense. How do we protect our hard-won metal from the elements? And more than that, how can we make it even better than it was in its natural state? Well, we have a whole arsenal of techniques. The simplest ones just create a barrier, right? Paint, oil, or grease. More advanced methods include galvanizing, where you coat iron with a layer of more reactive zinc, or anodizing. But maybe the most powerful solution of all is to fundamentally change the nature of the metal itself. And we do that by creating an alloy. Now, an alloy isn't just a simple mix. It's a whole new material, carefully designed by melting and mixing elements together to create something with far superior properties than the original pure metal. And there is no better example than iron. On its own, pure iron is actually pretty soft and not all that useful for construction. But add a tiny amount of carbon, we're talking less than 1% sometimes, and you create steel. Suddenly, the material becomes hard, strong, and perfect for building skyscrapers. That tiny change creates a completely new, vastly superior material. And that brings us full circle. Remember that ancient, rust-resistant iron pillar in Delhi? It wasn't magic. It was the result of ancient metallurgists who, through incredible skill and maybe a bit of luck, created a unique iron alloy with high phosphorus content. This formed a protective film that has shielded it for centuries. From their mastery to the advanced alloys in our jets and phones, the journey of a metal is really a story of human ingenuity. This entire process, by the way, is a huge part of the Class 10 curriculum. So if you found this helpful, make sure to subscribe to the A1 Institute YouTube channel for more explainers just like this one. It's about understanding the rules of nature and then using them to unlock, refine, and reinvent the very materials that shape our world. The only question left is, what will we invent next?